Hello and welcome. In this video, our goal is to find all the real roots of the cubic equation, a cubed minus 3a plus 1 equals 0. That's a cubed minus 3a plus 1 equals 0. By the end of this video, you will be able to solve a cubic equation that looks deceptively simple using a clever trigonometric substitution. This is a powerful technique for certain types of cubic equations. At first glance, this equation might seem straightforward. We could try rational root theorem, but we'd find there are no integer roots to simplify it. So, we need another approach. Today, we'll use a method that leverages a special trigonometric identity to find all three real roots. Our strategy relies on a key trigonometric identity. It relates the cosine of a triple angle to the cosine of the single angle. The identity states that the cosine of 3 times an angle theta is equal to 4 times the cosine cubed of theta minus 3 times the cosine of theta. This identity, the triple angle formula for cosine, is the heart of our solution. We're going to use it by manipulating our original equation to look similar to this identity. The first step to make our equation, a cubed minus 3a plus 1 equals 0, resemble the cosine identity is to get a 4 in front of the cubic term. We can achieve this by multiplying the entire equation by 4. This gives us 4a cubed minus 12a plus 4 equals 0. Now, let's rearrange this new equation slightly to group the first two terms together. We can write it as 4 times the quantity a cubed minus 3a plus 4 equals 0. If we now compare this to our cosine identity, we can see the resemblance starting to emerge. The expression inside the parentheses, a cubed minus 3a, looks very much like the right side of the identity, just without a cos cubed, or cos. This brings us to the key insight of the method, trigonometric substitution. We are going to make a change of variable to transform our algebraic equation into a trigonometric one. Specifically, we will substitute a with the expression 2 times the cosine of theta. Why this specific substitution? We made the equation look like 4 times a cubed minus 12a plus 4 equals 0 to match the structure 4 times cosine cubed minus 3 times cosine. If we substitute a equals 2 cosine theta, we can see how the magic works. Let's substitute a equals 2 cos theta into our equation 4, a backs 1-3a plus 4 equals 0. We get 4 times the quantity, 2 cos, th cubed, minus 3 times 2 cos, and then plus 4, all equals 0. Simplifying inside the parentheses, we have 2 cubed is 8, and 3 times 2 is 6. So we get 4 times 8 cos minus 6 cos plus 4 equals 0. Distributing the 4 gives us 3 2 cos, 0.234 cos plus 4 equals 0. This might seem more complicated, but watch what happens if we factor out an 8. We get 8 times the quantity, 4 cospect, minus 3 cospect, plus 4 equals 0. Now, let's look at the expression inside the parentheses. This is precisely our triple angle identity. 4 cos p theta minus 3 cos p theta is equal to cos 3 theta. By making this substitution, we've transformed the problem. Our cubic equation in terms of a has become a simple trigonometric equation in terms of theta. Now that we've made the substitution and simplified the expression, we have a much simpler equation to solve. Our equation has become 8 times the cosine of 3 theta plus 4 equals 0. This is a basic trigonometric equation. We can easily solve for the cosine of 3 theta. Subtracting 4 from both sides gives us 8 cos 3 equals minus 4. And dividing by 8, we find that the cosine of 3 theta is equal to minus 4 over 8, which simplifies to negative 1/2. So, our task now is to find all the angles, theta, that satisfy this equation. Remember, the cosine function is periodic. For any given value, there is an infinite number of angles that yield that value. Since our original cubic equation has at most 3 real roots, we need to be careful about finding 3 distinct values for a. This means we need to find at least 3 distinct values for 3000 that result in different cosines. Let's find the values for 3 theta. First, we find the principal value using the inverse cosine function. The inverse cosine of negative 1/2 is 2 pi over 3. This is our first solution for 3 theta. So, 3 theta equals 2 pi over 3. However, we need more solutions. The cosine function is symmetric about the x-axis. This means if an angle alpha works, then negative alpha, or 2 pi minus alpha, also works. So, our second solution for 3 theta is 2 pi minus 2 pi over 3, which equals 4 pi over 3. We need one more. The cosine function has a period of 2 pi. We can add 2 pi to our first solution to get another one. Adding 2 pi to our first solution gives us 3 theta equals 2 pi over 3 plus 2 pi, which is 8 pi over 3. If we added 2 pi again, we would get 14 pi over 3. The cosine of 14 pi over 3 is the same as the cosine of 2 pi over 3. So using 14 pi over 3 would not give us a new distinct root. For a cubic equation, there can be at most 3 real roots. These 3 solutions for 3 theta will give us exactly those 3 roots. Here are our 3 values for 3 theta, 2 pi over 3, 4 pi over 3, and 8 pi over 3. We've done all the hard work. Now, we just need to convert these back to our variable a. Remember our substitution. A equals 2 cosine theta. So, to find the roots, we calculate 2 times the cosine of the theta values we just found. First, let's find the theta values themselves by dividing each of our 3 theta values by 3. Theta 1 is 2 pi over 9, theta 2 is 4 pi over 9, and theta 3 is 8 pi over 9. Great, now we can find the roots of the original equation. The first root, a sub 1, is 2 times the cosine of 2 pi over 9. The second root, a sub 2, is 2 times the cosine of 4 pi over 9. And the third root, a sub 3, is 2 times the cosine of 8 pi over 9. These are the 3 exact real roots of the equation, a cubed minus 3a plus 1 equals 0. They are expressed in terms of cosines of these angles. While these exact forms are mathematically correct, they aren't the easiest to visualize. We can get decimal approximations using a calculator. The cosine of 2 pi over 9 is about 0.766, so a sub 1 is approximately 1.532. The cosine of 4 pi over 9 is about 0.174, so a sub 2 is approximately 0.347. And the cosine of 8 pi over 9 is about minus 0.940, so a sub 3 is approximately minus 1.879. So, let's recap what we accomplished. Our objective was to find all real roots of the equation a cubed minus 3a plus 1 equals 0. We achieved this by using a powerful technique called trigonometric substitution. By manipulating the equation to resemble a triple angle identity, we were able to transform it from a cubic polynomial into a simple trigonometric equation. We started with the cubic equation, multiplied by 4, substituted a equals 2 cosine theta, and the triple angle identity allowed us to simplify it to a straightforward cosine equation. Solving this equation for 3 theta, we found 3 distinct values. These led us to our final 3 real roots, expressed in exact trigonometric form. This method, sometimes called Cardano's method with a trigonometric solution, works beautifully for cubic equations with a repeated root, or for cases like this where the roots are all real and in a specific range. You now know how to solve a cubic equation using trigonometric identities. This demonstrates that there's more than one way to tackle a problem in mathematics, and sometimes the most elegant solutions come from unexpected connections. Thank you for watching.